This video covers general mechanisms for direct 1,2 reactions, which is covered in the first part of the carbonyl chemistry section of second year organic and biological chemistry. So the first reaction we're going to cover is 1,2 addition, and synthetically useful 1,2 additions are usually carried out under strongly basic, usually aprotic conditions. And that's because we're using very strong nucleophiles like organometallics and complex metal hydrides, which generally don't tolerate protons being around in the flask. Also, to get a 1,2 addition reaction rather than a substitution, we're going to have to use carbonyl compounds like aldehydes and ketones, which don't have any built-in good leaving groups. These R groups here are going to be carbonyl hydrogen based. So if we expose our carbonyl compound to our nucleophile, in this case an anionic one, the nucleophile is going to attack the carbonylic carbon, and we're going to push the electrons from the carbon-oxygen pi bond up onto oxygen, and that's going to get us to our first tetrahedral intermediate. If we're using something like an organometallic or a complex metal hydride, the mechanism will look something like this, where we're pushing a carbon metal bond or a hydrogen metal bond. But fundamentally it gets us to the same place, which is our tetrahedral intermediate. As with any tetrahedral intermediate, we need to consider the structure and what groups are attached to the central carbon. As it stands, none of these are good leaving groups. Our two R groups are either carbon or hydrogen based because they've come from an aldehyde or a ketone. And if we're using a strong nucleophile like an organometallic or a complex metal hydride, this group over here is going to be carbon or hydrogen based. That's going to be a poor leaving group as well. So this tetrahedral intermediate will persist until it's modified by the chemist. And that usually involves a second step, which is quenching with an electrophile. In the vast majority of cases, this is quenching with a source of protons, so a mild acid workup or water, but you can add in other electrophiles like alkyl halides if you like. So we're basically going to alkylate or protonate the oxygen, and we're going to end up with our addition product like this, and obviously if this was quenched with protons, this would then be an alcohol. So if we now carry out our reaction again under strongly basic aprotic conditions, but on a carbonyl compound which has a built-in leaving group attached, we're going to get 1,2 substitution rather than addition. So we're still looking at the same class of nucleophiles, organometallics, complex metal hydrides, etc. But this reaction now is going to take place on esters, acid halides and anhydrides, that sort of thing. So again, exposing our compound to the nucleophile is going to attack the carbonyl in exactly the same way. We're going to push the electrons up onto oxygen, and we're going to get to a tetrahedral intermediate. Again, if we're using organometallics, the mechanism is going to look something like this. So we consider the structure of the tetrahedral intermediate, look at all the groups that are attached. The R group is likely to be a poor leaving group. It's going to be something carbon-based realistically. The nucleophile is likely to be a poor leaving group if it's come from an organometallic or a complex metal hydride. But we've built in a decent leaving group into this molecule. If it's an ester, it's going to be an OR group. If it's an acid halide, it's going to be a halide, and so on. So our tetrahedral intermediate now collapses. The electrons from the oxygen lone pair push down and kick the leaving group out of the molecule. What makes it a good leaving group is the fact that it's a nice stable anion, so things like chloride and acetate and that sort of thing will obviously get eliminated from the molecule. And what we've then got is our substitution product, where we've started out with our leaving group attached and we've substituted it for the nucleophile, but we've gone via a tetrahedral intermediate. Now, it's useful to bear in mind that all of these processes are going on in the same flask, and what we've generated here is, if we're using an organometallic, say, it's going to be a ketone. And generally things like ketones are more reactive than things like esters, which we've just made it from. And we've got our nucleophile kicking around in the flask as well. The reaction doesn't go instantaneously to completion. So there is an opportunity for the product that we form, that we potentially want, to react again with residual nucleophile in the flask. So things like adding organometallics to esters to try and make ketones is generally unsuccessful because you tend to get this 1,2 addition product as well, or this double addition product if you like. So what if we want to use a slightly weaker nucleophile? So let's say an alcohol or an amine. Well, we can do reactions like this under weakly basic, potentially protic conditions, because we're now using nucleophiles which will tolerate protons being around, and in these cases actually bare protons themselves. So we need a carbonyl compound that has a decent leaving group attached. We're going to attack it with a nucleophile, but now we're going to add an exogenous base as well. And we'll see how that affects the reaction later on. So if our nucleophile is going to attack, in the case of an alcohol or an amine, it's going to have a lone pair, so it's going to attack into the carbonyl, exactly the same as we saw before, and we're going to push the electrons up onto oxygen. We'll end up with this tetrahedral intermediate. Now, considering the structure of this tetrahedral intermediate, we look at all the groups that are attached, and we have this hypervalent cationic group that we've just added in. This is our nucleophile that's just added into the molecule. Now, this is actually quite a good leaving group, because what the molecule wants to do is push the oxygen lone pair down and kick this back out again, and it will form this nice, stable, neutral molecule that we started with. But we don't want that to happen. We want to kick out the leaving group that we had in the molecule to begin with. So this is why we've added the exogenous base here. So the base now gets involved and deprotonates the group that we've just added. Now this gives us a new tetrahedral intermediate where the nucleophile group that we've just added is now a worse leaving group. It's no longer hypervalent, it's no longer cationic, so it's unlikely to be kicked out of the molecule. And the structure of this tetrahedral intermediate dictates that the best leaving group is now the guy that we want to leave, so therefore the oxygen lone pair comes down and kicks this guy out, and then we have our 1,2 substitution product. Now it's still worth considering whether your substitution product will react further under the reaction conditions, but this tends to be less of an issue when you're using weakly basic conditions as it does when you're using the really strong nucleophiles like organometallics. So what we can also do under these type of reaction conditions is if we've got a substrate which has potentially not a great leaving group attached, we can use the base as a sort of proton shuttle to transiently protonate this guy and encourage it to leave. So mechanistically speaking, let's add the nucleophile into the carbonyl, kick the electrons up onto oxygen, form a tetrahedral intermediate, make the group that we've just added a worse leaving group by deprotonating with a base, exactly the same as we did before. And we then end up with a tetrahedral intermediate where none of the groups that are attached are particularly thrilled about leaving. But you have a group here which has the potential to be a good leaving group by protonation. And we can use the conjugate acid of the base that we've just used to take this proton off to transiently protonate this guy. And we end up with a tetrahedral intermediate then which has a very good leaving group attached. The oxygen lone pair comes down, kicks this guy out, and we end up with our substitution product. So in the case of things like acid halides and anhydrides where your leaving group is going to be chloride or acetate, these are very good leaving groups. But in the case of some esters, so phenolic esters and that sort of thing, they're not great leaving groups to start with, but by transiently protonating them you can actually get them to leave and substitute. So we can also do 1,2 substitution under acidic conditions, and generally this applies to carbonyl compounds where the leaving group isn't great, and we need to encourage the leaving group to leave to become a better leaving group by protonation. So example nucleophiles are much the same as we had previously, but now we're looking at carbonyl compounds like carboxylic acids, esters, and occasionally some amides, where you've got a group here which is potentially a good leaving group, but not until it's been protonated. So the main difference between obviously basic and acidic conditions is we're going to have our nucleophile in solution, but we're also going to add an exogenous acid now. And this is the key difference between acidic and basic mechanisms, is that usually the carbonyl compound that you're trying to react isn't as reactive. So carboxylic acids, esters aren't as reactive as acid halides and anhydrides and that sort of thing. So they need a little bit of encouragement. And that's what the exogenous acid is there for. So the first thing we're going to do is protonate the carbonyl. And that's going to give us this protonated carbonyl compound here. With the oxygen being hypervalent and cationic, it's pulling electron density out of the carbon that's attached to the carbonyl, which is making it more electrophilic. So then our nucleophile can come in, much as it did before, attacking the carbon, push the electrons up onto oxygen, and we now end up with a tetrahedral intermediate where we have an OH rather than an O-, but the same sort of rules apply. We look at the structure of the tetrahedral intermediate. The group that we've just added is the best leaving group, so we need to do something about that. We can use the conjugate base of the acid that we've just used, or we can use a solvent if it's an appropriate solvent to remove this proton from here, make that a worse leaving group. We then need to make the group that we want to leave the best leaving group, and handily we've reformed our acid, so we can protonate, end up with a tetrahedral intermediate here where we have the group that we want to get out of the molecule as the best leaving group, as a good leaving group. We can use the lone pair and oxygen to kick it out. That gets us back to a protonated carbonyl compound, which we then just deprotonate to get to our substitution product. So we've ended up with broadly the same class of products. We've done the same sort of class of reaction. We've just done it under acidic conditions rather than basic conditions. Now the final reaction we're going to talk about is 1,2 condensation. And this involves using alcohols and amines, broadly similar nucleophiles that we used before, only now we're going to react with aldehydes and ketones. Because we don't have any built-in leaving groups attached here, and our R groups, these are all going to be carbonyl hydrogen based. What we're actually going to get to leave the molecule is the carbonyl oxygen. And the only way we can do this is under acidic conditions, or at least protic conditions. So we're going to add our nucleophile and an exogenous acid. We're going to protonate the carbonyl as we did before because we're under acidic conditions. Then the nucleophile gets involved, attacks the carbon, push the electrons up onto oxygen, get to a tetrahedral intermediate. As it stands, the nucleophile is the best leaving group, so we need to deprotonate to make it a worse leaving group. And now, at this tetrahedral intermediate, all of these are poor leaving groups, including hydroxide. But if we protonate the oxygen up here, we can make hydroxide into water, which is a good leaving group. And the nucleophile down here needs to have a lone pair of electrons on it. So this basically only works with things like alcohols and amines, where the atom that's directly attached to your carbon now has a lone pair. So we're going to use a lone pair from the nucleophile to kick water out of the molecule. That's our condensation reaction, loss of a small molecule. And we then end up with this positively charged double bonded species. So this could be a carbon-nitrogen double bond, it could be a carbon-oxygen double bond. What then happens to this is dependent on the reaction conditions and the nucleophile that you're using. But we need to basically get rid of this positive charge. So one thing that could happen is the same nucleophile or a different nucleophile could add in and do a 1,2 addition reaction. So we end up with something that's sp3 hybridized. Or we could get rid of the positive charge another way and end up with something which is still double bonded, still sp2 hybridized. So for an example, if this is a carbon-nitrogen double bond and this is an iminium ion, we have a hydrogen attached to nitrogen, so we can deprotonate this guy and we end up with a stable imine compound that we can then isolate. So this is basically how imines are formed. Conversely, if we have a carbon-oxygen double bond, oxygen obviously here is hypervalent and it doesn't have any hydrogens to lose, so the only way we can quench this positive charge on oxygen is by pushing a nucleophile onto the carbon and then pushing the electrons up onto oxygen, exactly the same way as we've done over here. So we need another nucleophile. That could be one of the same again, or it could be a different nucleophile, but we basically need to do a 1,2 addition type reaction, and we end up with an sp3 hybridized product, and this is basically how we form things like acetals.